Okay, so we have a theorem for finding extreme values. This is where we're headed. We want to be able to find all the absolute maxes and mins as well as the local extremum. That's the local maxes and mins for any function f of x. And so this comes out of the extreme value theorem. So the extreme value theorem says if you have a continuous function on a closed interval, you're guaranteed an absolute max and absolute min. It might be at the endpoints, it might not. It's somewhere in that interval, there's a highest y value and a highest low value, and there's an x value that goes with it. And so you're going to need to be able to at least state the x values that go with each of those, and in a lot of cases tell what the y value is. When we get into real-life applications of this, application of the derivative, you'll be asked, what is that y value? Because it might correspond to the maximum area, maximum volume, or minimum perimeter for a given area, that type of thing. So if f has a local extremum at C, then f prime of C equals 0 or does not exist. So here's how we bring the derivative into it. So you're going to be taking the derivative of the function, and you're going to be checking two different things. One will be, where does the derivative equal 0? Because those x values at which the derivative of the function equals 0 are what we call critical points. They are possible extremum. Possible extremum. There's another test you have to put in there to make sure. But they are what we call critical points. Now the beauty of calculus is that all of the critical points will happen either at the endpoints of the domain, or where f prime of C equals 0, or where f prime does not exist. That's it. So you don't have to worry about anywhere else on the domain. You're not guessing and checking all these different values. You're not having to try and get an accurate picture of it. We know, this is a theorem that comes out of the extreme value theorem, is we know that local extremum will happen either at the endpoints, which I left out of this, but at the endpoints, you always have to check the endpoints, or where f prime of C equals 0 or does not exist. And those are all the possible critical values. It's hard to appreciate that unless you see some functions at which you could have lots of possibilities. But it limits our possibilities to where the maxes and mins would occur. Is that clear? That's what this is saying. So a point C is a critical value if f prime of C equals 0 or does not exist. So we look at that. A local max or min can only occur at a critical value, which is what I just said. But not all critical values produce a local max or min. There's something else that needs to happen. It's either you're at an endpoint of a domain, and so you have a one-sided interval, or you have to demonstrate a change in sign. Okay, there has to be a change in sign in terms of the function increasing or decreasing. For example, our cubic function you might think that the derivative might equal 0 here where it kind of changes over. The truth is it does not. It doesn't end up equaling, let's see, it doesn't end up equaling 0 there. It ends up just constantly increasing. So it's like here you might go, well, is there a relative or local max or min here? And you end up discovering that no, there isn't, because it just keeps increasing. Even though it almost flattens out, it does keep increasing. So what needs to happen for there to be a local max or min is that there has to be a change to the left and to the right of that local max or min where the function goes from increasing to decreasing or decreasing to increasing. It can't just level out and then start going back up again. That doesn't count. It has to actually change. It can't just level out. So a local max or min can only occur at a critical value, but not all critical values produce a local max or min. So that's why I'm calling them potential maxes or mins. But we're going to find all the critical values first by taking the derivative, setting it equal to 0, and also finding where the derivative does not exist. We're going to also look at the domain of the original function. We have to know the domain of the original function. And any domain restrictions in the original function we also need to know, because those could be critical points as well. All right, so here we go. We're going to start off with this function. I put the step process up here. So this is example 2. Did you guys get all that written down here? So this is a key idea. Is a local max or min can only occur at a critical value. That's what this theorem is saying. But not all critical values produce a local max or min. I'll show you how we find all the critical values of next involves the derivative. So example 2, we're going to find the absolute max and min on the closed interval -1 to 1 of the function f of x equals e to the negative x cubed. I'll let you write down this step process here. Go figure, first semester calculus, we're going to take the derivative when in doubt. And then to find all the critical points, we're going to set the derivative equal to 0 and also find any places where f or f prime are undefined. So we're also going to look at f and see where it might be undefined. And then also f prime. In other words, we're going to make sure we understand the domain and on that interval, because I'm giving you an interval, not a domain. So I'm really giving you an interval here. We're going to graph this function. We'll talk about the domain of the function. And we'll talk about if there are any places where f is undefined. And then we'll take f prime and see if there are any places where that's undefined. So set derivative equals 0, find where f or f prime are undefined. And those are the critical values, critical points. So solutions and values where f and f prime are undefined are critical points. So anywhere where the derivative is 0 or where these are undefined, we're going to call those critical points. And then we're going to test those critical points as well as the endpoints. So don't forget the endpoints. You might want to put a little star by the endpoints. Students, what we forget to do sometimes is check the endpoints, because the endpoints are also possibilities for maxes or mins. And if you have your graphing calculator, why don't you go ahead and graph this thing so you have a picture of what it looks like. I don't know if you know, guys know if this has any restrictions, or is it a nice continuous function? All right, I'll pull this back up. Let me go ahead and graph this with you. E to the negative x cubed. Here we go. All right, so y equals, here we go. That's how you type it in. It looks like that. E to the negative x cubed. And we're going to graph this thing. I'll just graph it on my standard graphing window, number 6 here. So there it is, kind of a crazy looking function, but does it look like it's at least continuous on -1 to 1? Does it look like it's continuous over all real numbers? So looks like it's going to keep on going. So that's e to the negative x cubed. So there are no domain restrictions. There aren't any places where I have any kind of jump, reverse asymptote, things going on like that. As far as I can tell, there aren't any holes. I wouldn't necessarily see those on here. But I don't have any reason to believe that I have any holes here because I'm not doing any factoring and canceling out a bottom factor, right? That's what would produce holes. So there it is. That's e to the negative x cubed. So it looks like it's a continuous function on this closed interval, -1 to 1. So that guarantees me an absolute max and an absolute min. But I can't just plug in -1 to the function and 1 to the function because the absolute max and absolute min aren't necessarily at the endpoints. They could be. Okay, and at this point, what they're wanting us to do, we haven't talked about increasing versus decreasing or a change in signs, at least the way to do that with the derivative. But what they're asking you to do is to just find the y values at the endpoints and at any of the critical points and compare them all. And if you look at all the y values, it will be clear which y value is the highest and which one is the lowest. And you're going to list that coordinate as your max and your min value. So going back over here. Still maybe writing down these 4 steps here. You're going to take the derivative, set it equal to 0, and find where f and f prime are undefined. Okay, there isn't any place where f is undefined on that angle. Let's go ahead and take the derivative. So f prime of x, remember your rule for this guy?
It's e to the x times the derivative.
Yep. E to the negative x cubed times the derivative of the power. -3x squared. So there it is. That's my derivative. Just looking at that, are there going to be any undefined places for f prime? If you were in question, you could graph it, right? No, I mean this is just a parabola. This is an exponential function. Putting those two together, it doesn't produce any undefined places. So we're good to go there. So we need to set this derivative equal to 0 and then also check the endpoint. So let's go ahead and set this derivative equal to 0 and solve it. Here's where you might end up, they might end up having to let you use the calculators to do the algebra for this, but I think we can solve this. What does x have to equal here for this to work? Yeah, if we go to solve this, I mean you can do it on your calculator if you want. You go for it. Try to. You remember how to do this on your calculator? How to find the zeros? You remember how to do that? Okay, let's see if it. So our hypothesis is that x equals 0 make a 0. Okay. Are there any others? Is the question. Do you think there are any others? No, I hope not. Go ahead. Do you guys remember how to do this? So you're going back to your calculator. You're going to enter in negative. We can just fix this. Just tack on. Just tack on the -3x to the second to it. So there it is. You can go ahead and hit graph. Okay, so there's the derivative. And we're looking to see where the derivative is 0. Looks like it's 0 right here. What do you think is happening up here? Perhaps. As x gets really big, so right here, by the way, here's how we did this last year. Second, calculate number 2, the 0, left bound. You guys remember doing this? Let's just see if your hunch is right. There's a right bound here, and then a guess, and it's going to give us x equal. Oh, didn't like that. So you go through the second, I'm not going to do that, but you go through the second calculated process and you'll see that 0 is a solution. What do you think is happening here? As x gets really big, that's a horizontal asymptote. As x gets really big, right? So This doesn't mean that it's just camped at 0. Probably a horizontal asymptote. But we're only looking at this thing from -1 to 1. And so is it clear from -1 to 1, the only solution is when x equals 0? Remember, this is the derivative. So we're only trying to see where the derivative hits 0. Okay, and it hits 0, and I'm talking about a y value of 0, which is right here at x equals 0. So going back over here, we have one critical point at x equals 0. One critical point at x equals 0. So here's the deal. We've got to test this one critical point that we found by setting the derivative equal to 0. We do not need to test any undefined zones for f or f prime, but we do need to test the 2 endpoints. So we have 3 different points that we need to check. And what are we looking for at these 3 different points? What we're gonna do is find the y value first, and then we're gonna check to see of these 3 points which y value is the highest and which is the lowest, and then one will not fit either of those. Okay, so here we go. Remember, we're going back up here, back up into here. So f of 0 equals e to the -0 cubed, which equals, just like our picture showed on the first function, what's this? 1. So we've got one coordinate is 0, 1. That's the one we got from the derivative. Okay, and then we've got 2 other points we've got to check. F of -1 and f of 1, because those are the endpoints of the interval. Okay, so f of -1 gives me e to the -1 cubed, which is so -1 of e to the first, which is approximately what? 2.7-ish. So we've got that guy, and then I've got one more to check. Sorry about this. I ran out of room here. One more endpoint to check. Here it is, f of 1. And f of 1 is equal to e to the -1 cubed, which is equal to e to the -1, which is about 1 over 2.7, or about a third, about 0.3. How about that if you want a decimal to go with it? About 0.3. About 0.3. So, looking at those 3 possible points, what is the absolute max? What is the absolute min? Absolute max is what coordinate? I want the exact coordinate. Negative. Right here, right? 2.7 was my biggest y value. So the absolute max was -1, comma, e to the first, just e. And then my absolute min is what? 1 and e to the -1. And this problem, I believe I took right from a free response question on the AP exam. So this is one that they expected us to do without a calculator. And the reason they would expect you to do it without a calculator is that e and -3x² are both nice, continuous, smooth functions, okay? So putting those together in the derivative, it's still nice, continuous, smooth functions. So you know that the only critical points are going to be when f prime equals 0 and at the endpoints. And what was cool about this one, or what's interesting about this one, and probably caused a lot of students grief, is they didn't include the endpoints. And where do the maxes and mins happen on this one? At the endpoints, not at where the derivative equals 0. There's just so many problems that we practice, that's where it will be. Okay? So really good kind of problem here. I wanted to do one where I actually have like 3 of them here where the functions are a little more difficult. You're going to, when you get into the homework here, you'll see what I mean. As soon as you hit problem 11, you're going to run into derivatives that are like this. Okay? They aren't all going to be nice polynomials. Okay? The polynomials are the easiest ones to run into. Yeah, question over here?
How do we solve that algebraic
How do you solve it algebraically?
Yeah.
We kind of did. We did. I mean, oh, right here?
Yeah.
So what you could do is no matter what you plug in, just think about e to the negative x cubed. Let's just think about that for a minute. On negative 1 to 1. So let's go back to that one. It's hard to think about it. Let's look at it. How about that? So I've got second e negative x. So we graph that guy. Oops. To the power of 3. Okay. We graph that guy. This thing's always positive. It's always above 0. So it's no problem algebraically. You would need to maybe state this. I don't know that you would even need to state it. I mean, you would just say x equals 0. But here's how we know. Because this is positive right here, you can divide each side by that whole term. And so you're left with negative 3x squared equals 0. Divide by negative 3, still 0. Take the square root of 0, still 0. So x equals 0. So we can do that algebraically. Okay, does that make sense? So that's how. All right, next one here. It says find the absolute max and min. Are there any local extrema? We're going to add in there. Are there any local extrema? So here's our function, y equals 1 over square root of 1 minus x squared. They don't give us a domain, so we're assuming over the entire real numbers. Okay. I am going to graph it, just so we have a picture of what this looks like. But then we're going to go through it like we don't have the picture. So here we go, 1 over square root of 1 minus x squared. So just write this down. We're going to find the absolute max and min. By the way, can you use the extreme value theorem on this? I didn't list a domain. What's a reasonable domain for this guy? This goes back to last year. What do we have to do to find a reasonable domain? And then is the domain a closed interval? Yes, we set the bottom equal 0. Set the bottom equals 0. So let's find out what this means. So we're going to take, basically, it's the bottom can't be 0, right? So we need to find the places that would make the bottom 0. Can you do it just in your head, just looking at it? It would be whenever this equals 0, set this equal to 0, or this cannot equal 0. So what does x equal? We have 1 minus x squared equals 0. Let's write it that way. X squared would equal 1. What does x equal? Plus or minus 1. Right? So plus or minus, so you probably could eyeball that. Okay. So when I go to graph this thing, my domain will be such that that cannot be plus or minus 1. Now there's more to it. What about the square root part of it? It is an inequality. It is an inequality. So not only can x plus or it can be plus or minus. So think about it this way. It can't be plus or minus 1. Could you have values between negative 1 and 1? Would those work? Yes, because that would keep this positive. Could you have values outside of positive 1 and negative 1? Could you have like 2? Put 2 work in here. Just try it. Put 2 in. Right. 2 squared is 1 minus 4 is. Now you got to run into problems with the square root part of it, right? So not only can the bottom not equal 0, but we have an inequality. What is the inequality here? Yeah, it's an in-betweener. It's a compound inequality, and it's an in-betweener. Can it include 1 or negative 1? No. So my domain looks like this. It's this open interval, negative 1 to 1. There it is. That's my domain. Negative 1 to 1. Is it okay that x equals 0? Sure. 1 minus 0 squared is 1, square root of 1 is 1, you just get 1. So it's fine. But anything to the left of negative 1 or to the right of 1 won't work. Now, does the extreme value, back to my other question, does the extreme value theorem guarantee that there will be both an absolute max and absolute min for this domain? Think back to the EVT. What does the EVT say? If f is continuous on what kind of interval? A closed interval. Is this a closed interval? No, so it's not guaranteed. So there could be two. There could be both an absolute max and absolute min, or there could not be any at all. Or there could just be one, either an absolute max or an absolute min. So the EVT won't guarantee it, but we need to do our work here. So we're going to check to see if there's any undefined places between negative 1 and 1. Obviously, at the endpoints, it's not defined. But is there anything else between negative 1 and 1 where this is undefined? No, isn't. So the next step would be to take the derivative and see if when the derivative equals 0 or when the derivative is undefined. So let's go ahead and do that next. Are we okay with how I found the domain here? I think you could eyeball it. You're going to see the same types of things showing up. There'll be square root symbols that have to be positive. There will be rational expressions like this one that can't be 0 on the bottom. And the only other thing that will show up is, remember with logs, what's true about logarithms is the only other one that will show up. Logarithms, the argument has to be, can it be 0? Let me write this down. So let me show you something here. Like if I write down ln of 0, here's what I'm saying. E to what power equals 0? Can't do that. So it can't be 0. Could this be negative? Like ln of negative 2. That would be like saying e to what power equals negative 2. Can we do that? No. So do you remember the restrictions on ln or log? Doesn't matter if it's ln or log. It has to be the argument for ln of x. The argument x must be strictly greater than 0. But those are the only three. I don't know if you remember this from last year. There are only three restrictions that we talked about primarily, and they were logarithms must be strictly greater than 0. Square roots must be greater than or equal to 0. And then you can't have 0 in the denominator. So those are the three you have to check. And you should be able to visually check those. So get the domain first for the function if they don't give it to you. And then here we go. Derivative, y prime. Can we do y prime for this? I think before we do y prime, we should think of it like this. Let's rewrite this. So think of this as 1 minus x squared to the negative 1/2 power. That might help you. This is chain rule. I'm going to ask you something like this on the test. There will be a square root with a polynomial underneath it. So what does the chain rule say is the derivative of this guy? I think the one on the quiz I had was like 12x minus x cubed underneath the square root symbol, or a cubed root symbol, not a cubed root. Well, what's that? So what's the derivative of this guy? Remove the negative 1/2. Yeah. Drop the negative 1/2 out in front. Copy down what's in parentheses. Drop this down by 1 power. Times negative 2x. Yeah. Here's the thing: is they do ask some crazy to do this with some crazy functions on the AP exam. So my notes have I've gone with the crazy. Like in the beginning, they started with nice polynomial functions, which we'll do one actually at the end, but they aren't all polynomial functions. So let's simplify this a little bit. This is where it does make sense, I think, to simplify it before you go and try to set it equal to 0 and solve. I think it's easier if you simplify it first. So I can do a little bit of canceling. The negative signs cancel, the 2's cancel. I end up with an x over this. It's square root of 1 minus x squared to the 3rd power. Remember, the power and then the root. The root is on the bottom, just like roots of a tree grow into the ground. So the root is 2. It's the square root. And then the power, the 3, goes up here. And the negative moves it down. Yeah. No, there's no quotient rule. We're just using a chain rule. We're treating this like our variable.
Yeah, but you still need to put divided by the bottom value squared.
No, because I moved this up and made it a power rule.
Oh, you made it a negative one. Okay.
And that's probably easier than trying to use quotient rule in the original. Could you use quotient rule in the original? Yes. One of the terms will be 0, so you take derivative of 1, it'll be 0, and you'll exit out. I think it's easier to make it a power rule. So move it up and make it a power rule. So here's what I've got. What am I going to do with this thing now, according to
Slow it up.
set it equal to? See, right? Mr. Orris has a shirt like this. When in doubt, take the derivative and set it equal to 0. That's first semester calculus. There's a little more to it. You got to check the endpoints and check the domain. But set this equal to 0. Okay, and look what happens again. Okay, first of all, guys, can this ever be 0? Could this be 0 on the domain -1 to 1? That's where we are at. Are there any numbers between -1 and 1, not including -1 and 1, because there was an open interval, that would make that bottom 0? No. You could graph it and you'd see the graph is totally above the x-axis. Try it if you want. But graph it, you'll see that, I can do it right now. Square root of 1 minus x, it looks like this. Second square root of 1 minus x squared. Second, insert left parenthesis. To the third power, zoom, number 6. There it is. So totally positive, guys. You see that? Looks like a little between -1 and 1. So that means, algebraically, it's for James, I can multiply each side by that body. It's positive, so it's totally fine. So I get x equals 0. There's the algebra. So that's probably what you were going to want to do anyways. It's like the only option. So x equals 0. And so I've got a critical point at x equals 0. But not at, I don't need to check the endpoints. Why not? Okay, and then over here, same deal. There's a does not exist at 1 or -1, right? But I don't need to check those because those aren't even in the domain of the original function. So listen carefully, guys. Listen. The domain of the original function is where you would pull your x values to get a max or a min. So if you take the derivative and there are places where the derivative does not exist that are not in the domain of the original, you don't need to check those. So the only point I have to check is x equals 0. So x equals 0 will give me either a max or a min. So here we go. So where do I check the x equals 0? Where do I plug it in? The original problem. So plug into the original. So we've got y of 0. So y of 0 equals 1 over square root of 1 minus 0 squared, and I get, so at 0, 1, we have something going on here. The question is it a max or a min?
Yeah. I mean, you can hedge your bets.
Is it a max or a min? Well, we're gonna learn. But here's the thing. In the next section, I believe it's in the next section, we're going to learn on how to use the derivative to test on each side of that point 0. But you
value, like you plug in 1 and negative on the derivative. Negative on those.
You do. How did you know about that? That is where we're headed. I haven't talked about that yet, but that's true. So here's the deal, guys. So, you're right. So what we need to know is that we have this point 0, 1, and we need to know what's happening to the left and to the right of it. Like if you try some values to the left and it's lower than that, try some values to the right and it's lower than that, then it's absolute max, and vice versa. But you can actually test it with the derivative. So if you take got y equals 0 here, if you try a point like, I think this is what you were saying. You're right.
If the derivative is negative to the left, then it's going to be negative.
Yeah. Yep. So you've got to have, it's got to be negative to the left and then positive to the right, but yes. So 0, 1, let's just go ahead and look at the graph here of this thing, of the original. I think in the textbook what they do on these is they do let you use your calculator to kind of check it, but there's my critical point 0, 1. It's going to be an absolute max or min. I'm pretty sure listed in this first section until we talk about what Jeremiah is talking about here. But I'm going to just type in 1 divided by second square root of 1 minus x to the second. Oops. And then graph it. So what is it, an absolute min or max? Why are these endpoints not an absolute max? They're actually open circles. Does that make sense? It doesn't show on the graph up here. It looks like they could be closed, but they're open circles. So we have an absolute min at 0, 1. And you're either, at this point, guys, you're either going to do this by checking the graph, or I could show you the way, what Jeremiah is talking about is between -1 and 0, what's a point I could check in the derivative? 0.5, negative 0.5. So you could test y prime of negative 0.5 and see if it's positive or negative. So if you plug in, you'd still probably need your calculator to do this. So like if you can use your calculator to plug in negative 0.5, you can use it just as easily to graph and see visually if this is an absolute min or max. But you would test negative 0.5 in here. So you put negative 0.5 in here. We could probably think about it. That's going to make it positive 0.25, 1 minus 0.25. Cubit, it's positive. Cubit, it's still positive. Take the square root, it's still positive. 1 divided by a positive is still positive. So it's positive. And then if you check, so let's see, x y prime and negative 0.5. If you check the derivative with 0.5 in there,
The bottom's always positive.
it is.
So the top's negative, the bottom's positive. Top's positive, the bottom's positive.
Yeah. Oh, actually, this is negative here. Sorry. So this is negative. You wouldn't need a calculator. You're right. So this would be negative, and then if you test y prime of 0.5, you would get your positive. And so it's going like this, guys. Negative to positive, so that tells me it's got to be a min. But we haven't gotten there yet. Okay, we haven't gotten there yet. That's in the next section where they talk about the test. All right. A couple more to do here, and then I'm going to have you try these 1 through 10 in the last 20 minutes or 15 minutes class. So find all relative extrema. So guys, on this one, what does this mean? Can we apply the EVT to this? Yes. So in this case, there will be an absolute max and an absolute min. So on the closed interval, 0 to 5 pi over 4. So that's from about right here to 5 times 3 is 15. 15 divided by 4 is almost 4. So we're kind of going between here and here. We've got the function f of x equals cosine of x minus pi over 4. So write that down. Are there any domain restrictions for the cosine function? Are there any vertical asymptotes? Any jumps? Any holes? No, it's a nice continuous function. So go ahead and find the derivative. Yes, more good review here. What's the derivative of this thing?
The inside is 1.
What's the derivative of the inside though? 1. So it's negative sine x minus pi over 4. Good. That's it. Okay, times 1. Because the derivative of x is 1, the derivative of pi over 4 is 0, so it's just 1. Okay, here we go, guys. Hang in there. Set it equal to 0. And then how do you solve this thing for x? You do. You eventually first divide out the negative 1. Then take the inverse sine of each side. So take the inverse sine of each side. We're only looking from 0 to 5 pi over 4. So on the unit circle, from 0 to 5 pi over 4 would be just around over to here. Which is fair. So 0 to 5 pi, kind of weird interval, but that's the interval. 0 to 5 pi over 4. So inverse sine of 0, where does that happen? There's 2 places, at 0 and pi. So you've got x minus pi over 4 equals that, and then solve for x. So you got to add the pi over 4 over. So what are my 2 values of x that are critical points? 0 plus pi over 4, or pi plus pi over 4. So we've got 2 spots here. They are pi over 4 and 5 pi over 4, but here's the deal. Those are our critical points. Okay, those are our critical points. But one of them is already an endpoint. Okay, so that's convenient. So here's what we have to test. We have to test pi over 4, 5 pi over 4, and 0. Those are the 3 points we have to test. So the 2 endpoints and all critical points. It just so happens that this is both an endpoint and a critical point. Okay. So test f of pi over 4, f of 5 pi over 4, and f of 0. And so when you plug in an f of pi over 4 to the original, guys, this is not f prime, but f. So plug it into the original. What do you get? Cosine, yep, cosine of pi over 4 minus pi over 4 is cosine of 0. Cosine of 0 is 1. So I've got a coordinate at pi over 4, comma 1. What about 5 pi over 4 minus pi over 4? That gives me cosine of pi, which is negative 1. So I've got 5 pi over 4, comma negative 1. You guys good? Stop the little conversation. So we are plugging in, okay, just to review here. We're plugging in our critical points and any endpoints, because this is a closed interval. And that's going to give us our absolute max and absolute min. And then the third one could be a relative max or min. F of 0 equals what? 0 minus pi over 4. So we're plugging in 0 here. So cosine of negative pi over 4 is yeah, 2 over 2. So we've got 0 comma root 2 over 2. So what's my absolute max? What's the highest y value we have among the 3? to 1. So this is my absolute max. My absolute min is the 5 pi over 4, comma -1 is an absolute min. And for today's assignment, when they ask you, I don't know why they do a little bit of this in the textbook on 5.1, but you really need to just look at the graph to be able to tell what the third one is, because I haven't told you, we haven't gone over the test that Jeremiah was talking about. It's actually called the first derivative test. That's in the next lesson. So looking at the graph, go ahead and graph cosine of x minus pi over 4. So cosine of x minus pi over 4. Make sure you're in radian mode here. Cosine of x minus pi divided by 4. Zoom z trig is number 7. So what was that other coordinate? It was 0, comma root 2 over 2. So it's just this other endpoint right here. So it's right here. What's that going to be? It's the endpoint. Is it the lowest point on a small little open interval? It is, because remember, you're blanking out all the rest of this. Take all the rest of that out. So this is the lowest point on a little open interval right there on the left. And since 0 is included in the domain, it was a closed interval, that is a relative minimum. Okay, we'll talk more about that later. But you just have to graph it to see if it's the lowest point on a small interval. So this is a relative minimum. All right. So I want to look at one polynomial function. So we'll end with the polynomial functions are probably the easiest ones to work with, because polynomial functions are just a sum or difference of a bunch of polynomial functions, like x cubed plus 3x squared plus 5x plus 10. It's just 4 separate, nice, continuous functions. You put them all together, they're continuous. So super easy to find the derivative of those. Here it is. So it says find all relative extrema for the function f of x equals x cubed minus 3x squared plus 3x minus 2. I know the domain of this is all real numbers. There's no restrictions. So I can jump right into the derivatives. With your polynomial functions, you'll be able to do that. I'll let you write down the example, and then we'll go ahead and do the derivative. And instead of equal to 0. The hard part of this, to be honest with you, is that as soon as they bump it up to 4th degree, then your derivative is 3rd degree. You've got to use the rational root theorem to get all your critical points. So you really are going to have to rely on your algebra. And that does show up. And then there's some factoring on here. What if it can't be factored? And you got to use the quadratic formula to get your estimate of the critical point. But that's a thing still, yeah. Everything you've learned since Algebra 1 is still a thing. So with the polynomial functions, you'll take the derivative, and then you've got to use, hopefully, factoring. Most of the time, factoring is sufficient. Most of the time, they're cubics, and so when you take the derivative, it's a quadratic. That is factorable. Okay. But they do throw some at you that are 4th degree. Yeah. So you end up with a cubic polynomial. Rational root theorem comes into play. Uh-oh. So here we go. Derivative of this thing is 3x squared minus 6x plus 3. There it is. So set that equal to 0. We can simplify this a little bit more. I can divide out the 3, right? We've got 0 equals x squared minus 2x plus 1. That's interesting. So how does that factor? And then we'll get our solutions. So how does this factor? -1, x minus 1, x minus 1. So what are the solutions? +1. So x minus 1 squared, set that equal to 0. Now, if there were other factors, you would set each factor equal to 0 and solve. So x equals 1 is our only critical point. That's it. X equals 1 is our only critical point. So is it going to be a max or a min? I don't know. It does bounce. So this is the first derivative. So we found x equals 1 is a critical point. Here's the deal. If 1 is the only critical point, we have everything to the left of 1 or everything to the right of 1. Okay. So let's go ahead and just do our little test here. So if I think of it like this, we've got negative infinity up to 1, and then we've got 1 to infinity. And so this is kind of a precursor to the next lesson. A good test point in here might be 0. Okay, if I test f prime of 0, what do I get here? F prime of, say, 0. Does that give me a positive or negative here? Positive. And then if I test over here, a good test point would be 2. You get to pick whatever value you want to plug in. So we just find, so f prime of 2, what's f prime of 2 going to give me? 4, that's 12, minus 12 is 0, plus 3 is positive again. So here's the deal on this one. And then I'll graph it and I'll show you, I'll demonstrate it to you. Because there is no sign change, so because there is no sign change in the derivative, to the left and right of x equals 1, there is no max or min. And in this first lesson, I'm fine with you using your graphing calculator bunch. We will formalize this little first derivative test next time, but because there's no sign change, and I'm going to demonstrate that to you with the graph here in just a minute. So what you would do is just go ahead and do the graph. You can use this if you want. Okay? If that's the only critical point, you just do a test point in the derivative on each side, because for something to be a relative extreme, remember the statement I made earlier? If you go back to that statement, and I'll come back to this. So this one right here. A local max or min can only occur at a critical value. Remember that? So you get your critical values. That's the only possibility for a max or min, relative or absolute. But that doesn't guarantee that you have one. It says here that not all critical values produce a local max or min. So this is my example of that. Is you could have a critical point at x equals 1. It is a critical point, but it's not a max or min. So what's happening on the graph of this function? Let's look at it. This is the one I drew a picture of earlier. So x cubed minus 3x squared. We got You guys help me out with this. X cubed, I don't remember the rest of it, minus 3x squared. What was the rest of it?
Plus 3x.
Plus 3x minus 2?
Yeah.
Okay, so when I graph this, what's happening here is it goes level at 1, negative 1. It goes level. It has a derivative equal to 0. You with me? But this is not a minimum point. Okay? You guys with me here?
Yes.
This is not a minimum point because it doesn't actually dip down enough. Like I would have to stretch this thing this way. And there's ways to do that with a cubic polynomial to have a max and a min. But this one does not have a max nor a min. It essentially always is increasing. Yes, it levels out, but it never comes back down at all. So it's always increasing. And so that's a picture of a function that would have no relative extreme. Okay, no maxes or mins whatsoever. If I put it on a closed interval, it would have an absolute max and absolute min. But it does not have any local maxes. Okay. More on this next time. Go ahead and use your graphing calculators for this. When it says relative or local maxes and mins, you can go ahead and find the critical point, use your graphing calculator to decide for tonight's.